Hello everyone, let's come to lecture number 16. In our previous lectures we have been discussing on the possibility of formation of second phase, and in our situation what we have considered, that is a solid formation from a liquid composition. What we have observed that whenever we consider a particular composition of liquid, that particular composition on that G2 line of that liquid, we have to draw a tangent, and then we have to see that the part of that tangent, whether that part would be higher up than the solid G2 line, and then only there is a decrease in free energy for the formation of solid from that particular composition of liquid. And in why we are drawing that common tangent? This common tangent is indicating that any composition can be reversibly formed from the base composition of the liquid, and then we are getting equilibrium transformation from that particular composition to some other solids. So, what we have seen, if we draw the free energy composition graph, so if this is my liquid line, this is G2 of liquid, and if we consider this is to be my G2 of solid, and it is at a particular temperature T and pressure, the equilibrium compositions can be seen from common tangent on both the free energy lines. And this is my equilibrium X B liquid, and this is X B solid. And in our last lecture what we have seen, that if we take composition left to this particular composition, then no solid would come out, because every time if I draw a tangent, let us say here, if we draw that tangent, this tangent would be always below the G2 line of solid. So, in order to form solid, we have to increase the free energy, which is not thermodynamically possible. But if we take any composition on the right side of it, of the liquid, because initially everything was liquid. So, let us say if I take a composition, this one, this is X0. When we get this composition, then as per our concept, we have to draw a common tangent. If we draw it with blue color, so then the common tangent would pass through this. So, this is my mu B of liquid, and this is mu A of liquid, and that time composition equal to X0, and this is also composition equal to X0. And then we are saying that from this composition along this particular free energy line, which is drawn at the intersection point of X0 and G2 of liquid, I can transform reversibly. That means every time I will maintain the equilibrium, this if I follow through this particular line. Now while doing that, I could see that this point and this point, between these two intersection point, I see that every time I could get a solid, because free energy difference is negative for the liquid line. This is basically the liquid line, this tangent, and solid line, which is G2 of solid. So solid nucleation is possible. Now if I try to see what should be my free energy difference for the equilibrium, that means if this particular composition has to come out from that particular liquid, so my free energy difference is this one. So this I can give a name which is called delta G n, and this n I am mentioning, this n indicating nucleation. We are saying that if I have to get this solid of this composition, this should be my free energy difference, which will be driving that particular transformation. So remember, this particular value is value required for driving nucleation of solid of this composition. But if I try to see the overall transformation free energy change, because finally we would get this composition and this composition, because this particular composition will distribute between XB solid, XB liquid, these are the equilibrium composition at that particular temperature. Finally we will get this composition and this composition of liquid and solid, that is fine. So if I try to see what will be the global free energy difference, the global free energy difference is coming, this difference is the global free energy difference. So I can term it as delta G, I can say delta G prime. So delta G prime is global free energy difference for getting liquid of composition XBL and solid of composition XBS. And here also you see that actually we are reducing the free energy, because from the liquid line to this point I am reducing the free energy. So that transformation is also thermodynamically feasible. So we have two free energy term, one is delta Gn, another one is delta G prime. This is nucleation driving force, and this is a global transformation driving force. This term will be applicable while considering the nucleation phenomena or nucleation rate. This is nucleation rate. That time we have to consider delta Gn, and this term will be part of delta G star, which is activation energy for nucleation. I mentioned before that delta G prime will be effective for overall transformation. Overall transformation. So we will see that. Now coming to the discussion what we have done in our last phase of lectures. So there we have seen that delta G star can be indicated with this particular formula, gamma 3 divided by delta GV minus delta Gs square. And remember, that time we have considered precipitation of beta phase. We are going little away from the solid liquid transformation. The solid liquid transformation actually is indicating that when we would have nucleation of solid, similar phenomena can be active while solid liquefaction from another solid. So now in this case our diagram, phase diagram was so this is, let us say I am considering beta phase formation. So this is solvus, this line is solvus, line, and this is x beta, and if we start with a composition x0, and at this temperature my composition should be x e, and this would be my x beta, and this is my alpha and alpha plus beta. So this is my equilibrium temperature Te. If you go back to previous lectures of phase 1, you would see this phase diagram was considered while considering precipitation of beta phase in alpha. And that time, since it is a solid transformation, then delta Gs is strain energy part. And strain energy is coming because there will be always some sort of lattice mismatch between the parent phase and the product phase, that means the precipitate which is coming out of alpha phase. So this term is a positive quantity. Delta GV is the driving free energy for nucleation. Gamma is solid or alpha beta interfacial energy. And in this case, if I try to see the delta GV, then we have to draw free energy composition diagram of alpha and beta. So if I see the free energy composition diagram of alpha and beta, since beta is almost about a single composition, there is not much of variation of beta line with change in temperature. So it would be a very narrow change in free energy. This is G2 beta, and if I try to see alpha, alpha line is this one, this is G2 alpha. Now equilibrium composition at that particular temperature. So this was my x0, that initial composition, this is xe and this is xb, which is corroborating to this compositions as per the phase diagram. Now at this point, if I draw a tangent, so in order to form this particular composition, my free energy gradient would be this much, which is nothing but delta Gn as per our previous concept. Now if we consider, this is basically the molar quantity, that is free energy in joule per unit mole. In order to we have to convert everything into volumetric term because these terms are considered with reference to volume, per unit volume. So then delta GV can be written as delta Gn divided by Vm. And this Vm, we are assuming that solid or liquid, both the solids have almost similar molar volume. This is an assumption which may not be true. This is done just to make calculation simple. So this delta GV term is coming, we could do the calculation by considering the free energy line equation of alpha, free energy line equation of beta, and then finding the equilibrium composition from the concept of chemical potential, which is at this point mu A of alpha equal to mu A of beta, and here mu B of alpha equal to mu B of beta. So these concepts we can follow up, and we have done the calculations while doing the isomorphous phase diagram from thermodynamic principle. So we can easily get those 2 points by solving these two equations, and then at this point we can also draw a tangent, and then that tangent we can get the cross section of that tangent with the free energy line of beta, and then measurement of this particular value delta Gn, and then dividing it by molar volume we can get delta GV, which can be used up in this particular equation. Delta GS term, how do we calculate it? We will show it in next few lectures, but for the time being we are bothered about this particular value, and these value will be used up for calculation of N. And if we see our previous discussions, we could get IN, which is the nucleation rate graph from this schematics. So this is my T versus percentage of B, this is the composition we are talking about x0, and at this point we are getting, this is my XE, equilibrium composition of alpha, this is alpha plus beta. So this is my TE, this is the equilibrium temperature. Now since there is a contribution from strain free energy, so that is what we will not experience the total free energy change to be this. The total free energy change will be actually coming from this difference. This difference gives me the total free energy change, and since delta GS term is positive in nature, so it will actually reduce the driving force, and if the strain energy term reduces the driving force, then we have to go further undercooling in order to get solid formation. That means the second phase formation, in this case it is beta. So that case this is my TE, actually delta GV varies this way, and there is a positive contribution from delta GS term which actually reduces the free energy term, and if we consider that delta GS term is constant over the entire temperature range, so I would get another line which is my effective free energy driving force. So this difference is delta GS, and if we try to measure delta G star, which is 16 pi by 3 gamma q delta GV minus delta GS square. So, now actual transformation start temperature would be this one, which is T actual, this is T E equilibrium. So, delta G star would follow this particular line. From that, so that means any transformation which would take place, which would be between this point to below point. So, till this range we will not get anything, because that time I am seeing that the total driving force is not sufficient for any transformation, because that time delta Gs term is more than delta Gv term. So, actually we are not getting any driving force for transformation. So, now similarly I can get the plot between exponential minus delta G star by kT as well as exponential minus delta Gm term kT. See, this delta Gm term is coming because if we have two atoms, so then when there is a jump between one atom to another atom, so we are going via a barrier. This barrier is delta Gm, which can be obtained from diffusion constant d equal to d0 exponential minus delta Gm by kT. So, this way we can get, this is diffusivity of that second element, that means the solute element, which is nothing but the B. So, we will get to see this is my T, this is my T actual, from where nucleation is possible, because then from that point onwards we are getting effective driving force, which is negative. So, we will get so this is my exponential minus delta Gm by kT, and this is exponential minus delta G star by kT. So, my n would be, we also I would be I0 exponential minus delta G star by kT plus delta Gm. We have already seen this particular equation. So, this would be lying between this line. So, this line is nothing but this. So, we are getting nucleation rate, and remember, while calculating nucleation rate, apart from gamma and delta Gs term, delta Gv term is also very important. So, we see that nucleation rate can only be quantified if we know gamma, delta Gv and delta Gs. Now, let us see what would be the effect of this free energy driving force for the growth rate. We can also have an impact on growth rate. We have already seen from our previous discussion that if we have a slab, so this is X, so this slab is forming, which is beta phase, and this is my composition of C beta, and I am considering all the composition in terms of C, which is molar composition. So, that means mole per unit volume, mole per meter cube. So, then this composition is Ce, and the base composition is C0, which is equivalent to X0, this is equivalent to X beta, and this is equivalent to X E as per the phase diagram what we have drawn. And then the diffusion takes place from the bulk composition X0 B goes to the surface of the beta phase, which is nucleating from alpha phase of composition X0, then we can get an equation for V, which is the growth rate, equal to d del C0 square 2 C beta minus C beta minus C0 x, this is the distance, and that time if we consider that the molar volume does not change and molar volume of alpha and beta both are similar, then we can write mole fraction would be equal to molar composition into molar volume. So then I can replace this with V equal to d del x 0 square 2 C beta minus C beta minus C0 x, sorry, now everything would be converted into composition of mole fraction. So this is x mole fraction. So finally we get V equal to, after doing little bit of reshuffling, then we get x0 x beta minus xe root over d by t del x 0 divided by 2 x beta minus xe root over dt, and that time we are assuming xb minus xe is equal to x beta minus x0. So then only this particular thing is possible. So now here also if we could see from this diagram, del x0 is nothing but x0 minus xe, and also we can prove that particular part delta Gn is proportional to delta x0 or delta Gv proportional to del x0. Here also we are seeing that free energy term for nucleation is proportional to the composition difference between the base composition where we have started and the equilibrium composition of alpha phase at a temperature where we are doing the transformation of beta phase from alpha phase. So that proves that this particular term is extremely important in order to get an idea of growth rate and nucleation rate. Let us stop here. We will continue our discussion in our next lecture. Thank you.